Welcome back, everyone. In this lecture, we're going to introduce you to the t-distribution as well as two types of t-tests that we will be covering this semester. So far, we have learned the basics of hypothesis testing, inferential statistics, and we've also learned how to go through a z-test for one sample mean. The t-distribution is going to be the next step in our learning and understanding of inferential statistics. For this lecture, I would encourage you to take a look at Chapter 5, Module 10, pages 155 and 156 of your course textbook, Edition 4, as well as to start to peruse or look through Chapter 6, Module 11, and Module 12, as these will be useful not only for this lecture, but also for the next couple lectures. Let's go ahead and get started. Move to the next slide. Okay, introduction. We began our exploration of inferential statistics with the standard normal curve, the z-distribution. We talked about how to compute z-scores, we talked about relative standing, we talked about area under the curve using our area under the curve chart. We also did a z-test for one sample mean using those skills and those fundamentals for conducting an inferential test. In order to conduct a z-test for one sample mean, the one that we started with, we needed to know two things about the population that our sample data were being compared against. We needed to know the population mean as well as the population standard deviation. Now, however, in most research, we don't have access to population data. Usually we're comparing one group or one part of our sample versus another part of our sample, or we're comparing multiple samples together. And the key word that I'm saying here is sample. We usually only have access to sample data. We rarely have access to population data. So now we need to take a step forward in our understanding of inferential statistics and see what do we do when we don't have access to population data. So the bottom line that we ask here on this slide is, what types of inferential tests do we use when we only have access to sample data? Well, let's go ahead and introduce ourselves to the first series of tests that we can do. And those are going to require the use of a new distribution called the t-distribution. Let's move on to the next slide. The t-distribution. The first inferential test we'll cover that assume we only have access to sample data are the t-tests. These tests are based upon the t-distribution. So what is the t-distribution? All right, let's break it down by looking at the points of this slide. The t-distribution is a single parameter distribution that was derived from the z-distribution. Okay? Another bullet point. The t-distribution has a lot of similarities with the z-distribution, but it is dynamic. In other words, it changes shape. Okay, let's break some of that down. What do I mean by it's a single parameter distribution? In order to understand the t-distribution and what we're working with, we need to know one thing. That one thing is known as the degrees of freedom. And I'll go over that in a little bit more detail in a later slide. So keep that in the back of your mind. We need to understand this new concept known as the degrees of freedom. I also say that the t-distribution was derived from the z-distribution. What the heck does that mean? Well, a guy named Gossett, and this is back in the early 20th century, worked for the Guinness Beer Brewing Company, and they were doing sample testing with beer. And one of the things he realized was you can't use the concept of the z-distribution and the area under the curve that we've been working with so far, that area under the curve chart that we've been looking with. It doesn't hold up when you're working with small sample sizes. So he adopted the characteristics of the z-distribution to create a distribution that was compatible with sample data. And the result was published under the name Student's t-distribution. Now, why Gossett chose to write it and publish it under an anonymous name called Student, I don't know. But for right now, if you ever hear the name Student's t-distribution, it all refers back to this guy who worked for a Guinness Beer Brewing Company. Okay, so the other thing I say here is that it changes shape. What the heck do I mean by that? Well, the z-distribution the one that we've worked with the last couple weeks, you may recall, and we have a handout and we have a chart that has area under the curve, so we know for any particular z-score, we can figure out the area below that value, above that value, etc. Well, because the t-distribution relies upon sample data, it moves. And it moves based upon the sample size that you're working with. And as we'll see in the next couple slides, sample size is going to be closely tied into degrees of freedom. So because we work with different size samples from one study to the next, the t-distribution actually changes its shape. And you'll see an example of that coming up too. And this will have an impact, obviously, on the critical value. You may recall in the z-distribution, because it was a fixed normal curve, when we had an alpha of 0.05 for a two-tailed test, the critical value for z was always plus and minus 1.96. Well, the t-distribution, it moves. It moves based upon sample size and degrees of freedom, so that leads to the critical value changing depending upon the degrees of freedom, aka the sample size. So let's delve a little bit deeper into that. Move on to the next slide. So what are the similarities between the z and t distributions? Well, the t distribution, similar to the z, is symmetrical, unimodal, bell-shaped, and has a mean of 0. It's a derivative of the z distribution. So the t distribution, if you just looked at it as an outsider and I drew it on the board, you would say, oh yeah, it's a bell-shaped, unimodal, symmetrical curve and with a mean of 0. So that's where the similarities lie. However, the t-distribution is a bit different. Why? Because it's dynamic. It moves. So let's move on to the second bullet point down here, how the t-distribution is different. The t-distribution will become wider or narrower based upon the degrees of freedom. We mentioned that in the last slide. We must know the degrees of freedom in order to know the exact shape of the t-distribution we're working with. So, okay, let's take a look at what the heck do I mean by degrees of freedom. So, the degrees of freedom, as you'll see here written in red, the degrees of freedom are closely connected to sample size. What do I mean by that? Let's take a look at a formula for the degrees of freedom for one of the t-tests. So at the bottom of this slide, you see example, degrees of freedom for an independent samples t-test. And you'll notice, and degrees of freedom is abbreviated as DF. You'll notice that it says N1 plus N2 minus 2. Well, we know from previous lectures that N simply means sample size. So in an independent samples t-test, as we will learn shortly, it's when you're comparing two different groups. So we have group 1, N1, and then we have group 2, N2. And then in order to figure out the degrees of freedom for that test, we take the sample size of group 1, N1, plus the sample size of group 2, N2, and we subtract the constant 2. So this is what I mean when I say that the degrees of freedom are closely connected to sample size. Sample size is a huge part of the overall formula for the degrees of freedom. Let's go ahead and move on to the next slide. In this slide, we can take a look. What you see is an illustration down on the lower right side, which shows several different normal, symmetrical, unimodal, bell-shaped curves. These illustrate how the t-distribution moves, or as I said before, how it's dynamic, how it changes shape, depending upon sample size, or otherwise known as depending upon degrees of freedom. So what we see on this slide is as the degrees of freedom change, the critical values for the t-distribution will also change. So one of the things that may help you out here is this slide is sort of a snapshot of some examples of how the t-distribution moves. But also, if you look on Beachboard, you'll notice that I posted something that the area under the curve chart. But I think I combine it with the t-distribution. I think it says like z and t distribution. You can find that there. And there's one slide that shows you this in a little bit more detail about how the critical values move for the t-distribution. Okay, so all that aside, let's take a look at this one. When we have small sample sizes, the shape of the t-distribution tends to be wider and flatter than the standard normal curve. So if you look at our illustration on this slide, you'll see the one curve that says t with the degrees of freedom equal to 5 is the widest and flattest curve in that illustration. And you'll notice, how does that impact the critical value? Well, the critical value is all about at what value in that distribution is there 5% of the total area under the curve beyond the critical value. Well, if the curve itself is flatter and wider, then that pushes the critical values further out from 0. And if you look at the chart on the left-hand side, where it has the df, degrees of freedom, and then you'll see that they increase as you go down there. These are just some examples. And then the corresponding t critical values that go along with it, you can see this trend. So when we see a degrees of freedom of 5, the critical value is not at what we are used to of a 1.96. No, it's not going to be, because they're going to be further out into the tails. So at a small degrees of freedom, such as 5, you'll notice that the t critical value is plus or minus 2.57. If we increase the degrees of freedom just a bit, say to 13, which is the second line that you see, or the second curve that you see in the chart on the right, that reduces the critical value. It brings it in a little bit to make it start to look more like our standard normal curve. So when the degrees of freedom increase to 13, the critical value drops to plus or minus 2.16. And as we sort of march down that list to a degrees of freedom of 20, 25, 30, 60, you can see that the critical values get lower and lower and lower. And eventually, once you have a sample size that is very large or almost the same size as the actual population that you're studying, you'll see that the t distribution starts to mimic and look just like the z distribution. And that's where you see the infinity symbol, where it says that once you get a degrees of freedom that are at infinity, or you're not going to reach infinity, but more appropriately approaching the true population size, sure enough, the t distribution will start to look exactly like the z distribution. And that's why at the bottom of this, you see when your degrees of freedom get extremely high, your critical values will reach 1.96, just like they were with the z distribution. So the key takeaway here is the understanding of when you have low sample sizes or low degrees of freedom, because remember, degrees of freedom and sample sizes go hand in hand, as we saw from the previous slide. So when you have low sample sizes or low degrees of freedom, the shape of the t distribution is going to be wider and flatter, which causes the critical values to be further out into the tails. As the degrees of freedom and sample size increase, the t distribution starts to look more and more and more like that standard normal curve, aka the z distribution, and you see that those critical values start to get lower and lower and will eventually get to that 1.96 that we looked at before. So that's one of the key takeaways that we need to understand about how the t distribution is different from the z distribution, and this important role that degrees of freedom play. Let's go ahead and move on to the next slide. So in the next lecture, we will start to introduce you to the first t-test that we will be covering this semester, and that is the independent samples t-test. But in this lecture, I just want to give you a brief introduction to what the heck is the independent samples t-test. Okay, what's the logic of it? So as we go from one inferential test to another for the rest of this semester, I'm going to start off with what we see here in blue, the when to use. When do I use that test? Because I think one of the most important things with any understanding of inferential statistics is, when do I use a particular test, or why do I choose this test over that test? And that's going to be sort of the logic we've got. So you're going to see this sort of framework, and the setup of slides are going to be very similar. So when do I use the independent samples t-test? Well, as we can see here from this bullet point, let's read through this. You use the independent samples t-test when you're looking for differences in a continuous dependent variable between two independent groups. The two groups represent the two categories of the independent variable. Okay, what do I mean by all that? A nice way to break this down is to think about, in a research question, we have a cause and an effect. We have an independent variable and we have a dependent variable. And I think that's a nice way to sort of set these up and make a better understanding of them in a class like this. So what I've done is I've broken apart between the IV, the independent variable, and the DV, the dependent variable. So for an independent samples t-test, the independent variable must be a categorical variable that is limited to two categories. And you're going to see me throwing around multiple terms. So I mentioned the term qualitative, going back to what we talked about at the beginning of the semester. Categorical. Another term, two other terms that we don't have listed here are thinking about levels of measurement. That independent variable would have to be at the nominal or ordinal level, right? You may recall we talked about nominal and ordinal levels of measurement fall underneath that qualitative heading. So our independent variable for an independent samples t-test must be at the nominal or ordinal level, and it is limited to only having two categories. And we're going to see some examples here in just a moment that kind of illustrate that. Then we want to see a dependent variable, and that dependent variable must be continuous or quantitative. Thinking back to levels of measurement, what that equates to is meaning that it is at the interval or ratio level of measurement, right? So quantitative was interval ratio, so that's where our dependent variable has to be. So to recap quickly, in an independent samples t-test, the independent variable must be a qualitative variable that is limited to two categories. The dependent variable must be a quantitative variable, and that's what we're going to see in our examples. So let's take a look at a quick example here. Somebody raises a research question: is there a significant difference in midterm scores between men and women? This would be appropriate for an independent samples t-test. Why? Because we're trying to see, does gender have an influence on your midterm score? And let's see how these fit the when to use criteria. Gender is our independent variable. We want to see, does gender have an influence on midterm scores? Well, gender, at least in this scenario, might be measured as a dichotomous, categorical, qualitative variable of male, female. Two categories. And you'll notice that we have it set up that way. And our outcome, our dependent variable, is your midterm score. And your midterm score will be scored on a continuous scale, whether it's how many points you got out of 35 points, which is the example for our class, or whether it was out of your percentage out of 100, but it's at that quantitative or continuous level. So when you raise a question that says, I want to see, is there a difference between this group and that group on some continuous outcome, an independent samples t-test might be what you're looking for. So let's go on to the next slide and look at just a couple more examples about this. So move on to the next slide. So just a couple more examples. So here I just throw up a couple ideas to give us an idea of where we would use the independent samples t-test. So the first example raises the question, is there a significant difference in the number of marshmallows per scoop between two types of cereal, right? I mean, we're all staying at home right now and doing stuff like that, and I don't know about you, but we stock up on cereal just to feed the kids or have something, that won't go bad. So I thought this question might be, somewhat relevant here. So let's think about this. Is there a significant difference in the number of marshmallows per scoop between two types of cereal? So think about whether it's Lucky Charms or some other cereal that's got some treats in it, or maybe it's Raisin Bran, you're looking at raisins, whatever, it doesn't matter. Let's say that we have two types of cereal, type A, type B. And then we want to say, does one of them, would I rather buy type A or do I want to buy type B? Which one has more marshmallows per scoop? So I could do a t-test where I break it down where I've got two types of cereal, type A, type B. So once again, it is a qualitative, categorical, independent variable with only two categories. And then my outcome that I'm looking for to see if there's a difference between these two types of cereal is the number of marshmallows per scoop, which would be a quantitative or continuous or interval ratio level measurement variable. Now you'll notice I'm limited to only two types of cereal. So if somebody came along and said, well, I have type C or type D, a third or fourth type of cereal, and they say, I want you to compare across 3 or 4 types, we would have to stop and say, no, that is not appropriate for a t-test. A t-test always comes down to comparing 2. And I think the T is a good way to sort of remind yourself, T for 2. You're comparing 2 different groups in any type of t-test. So once again, the type of cereal, we have 2 types of cereal. They create the categories of our categorical independent variable. And then our quantitative dependent variable, number of marshmallows per scoop, would be measured. All right. Our bottom example is, do walking patrols by law enforcement officers influence crime rates? So some of you may recall from other classes that you've taken that there's been efforts around the world over the last couple decades of, can we improve community relations? Can we reduce crime rates by having law enforcement foot patrols or having our law enforcement officers get to know the neighborhood as opposed to simply driving by in their cruisers? So imagine we were doing a study like that where we set up 2 different type of law enforcement strategies in competing neighborhoods. In one neighborhood, we included regular walking patrols. So you'll notice when you look at my independent variable for this, where I say type of law enforcement patrol, the first category of that independent variable says walking patrols are included. The second would be sort of our control group. The second says, oh no, this is just good old-fashioned cops doing their drive-bys and driving patrols and riding around in their cruisers, looking out their windows, et cetera, right? So we've set it up where we have 2 examples of law enforcement strategy. One that includes walking patrols, a second that only includes driving patrols. So we've created a categorical independent variable, only 2 categories, and then the outcome, the dependent variable that we measure, is number of crimes committed per 100,000 citizens. So that may be a typical way that we would measure the crime rate to see, is there a significant difference in walking patrols versus driving patrols only? And then making sure that the independent variable is categorical, 2 categories, and the dependent variable is a continuous variable measured at that interval or ratio level of measurement. All right, so that's a brief introduction into the independent samples t-test. In our next lecture, we're going to go into much more detail and go through a couple of examples, but for right now, that's just sort of the setup. Let's take a look briefly at the other type of t-test that we'll be covering this semester. So let's go ahead and move on to our last slide. So on this slide, we talk about the second type of t-test we will be covering, which is known as the paired samples t-test, otherwise known as the dependent samples t-test. It goes by a few different names, but the idea is it's anything but independent. So it's the paired or dependent samples t-test. So why is this different or similar to the one we saw before, the independent? Well, let's take a look at the when to use. So to use this type of test, we're going to use it to examine differences between samples, and here's the key point, where observations in one sample can be paired with observations in the other sample. So the words independent and dependent are going to be key things that define the difference between this test versus the independent samples t-test that we talked about on the previous slides. So on this one, we assume that observations in the 2 groups or the 2 samples, depending upon how you're thinking about it, are paired or correlated or associated with one another. All right, so let's take a quick look at it and we'll go through a couple of examples. All right, so in this one, for the paired samples t-test, the dependent variable, once again, has to be continuous or quantitative, just like we saw before. But the independent variable, it's not quite as easy to describe as it was for the independent samples t-test. So I think examples will give us a better idea of how to understand how we break apart the independent and dependent variables. And remember, it's a t-test. We're still comparing two, t for two. Remember that, t for two, comparing two groups. But in this case, the two groups are correlated or dependent upon one another. All right, so let's take a look at the examples. So the first example we have here is we might design a study where we have a longitudinal pre-test, post-test of the same subjects. So when you took a research methods, or when you do take our research methods course, you'll understand the idea of like understanding a experimental study where it's a pre-test, post-test, where we want to say like, okay, let's do a baseline of, say, how well you perform on a certain subject, and then we send you to training to get you better in that subject, and then we do a post-test to see, have you gotten better, right? Or if you're working out with a personal trainer, they may say, well, how many push-ups can you do? And then you measure how many push-ups you can do on day one, and then you go through their 6-week, training program, and at the end of those 6 weeks, they say, well, how many push-ups can you do now? Pre-test, post-test, right? That's kind of the logic of a common way that we use this paired samples t-test. So in this case, the dependent variable is still going to be continuous. So it may be how well you perform on a particular topic, how many push-ups you can do, something that is measured in a continuous fashion. The independent variable would be whatever is inserted. Did you take a class? Did you get training? Did you go through some sort of education that occurred between the pre-test and the post-test? A common way that I've used this in the past, unfortunately we won't get a chance to do it this semester, is I've had students sometimes in the first day of my stats class come in and I give them a multiple choice exam on the first day. They've never taken anything that I've taught them statistics based at all. And they take it and they get a score. Then we go through a semester of learning statistics. And at the end of that semester, I give them the exact same multiple choice test again. So that would be the post test at the end. And then I compare the differences in their score to figure out, have they learned anything, or what have they learned throughout the course of the semester? Was I teaching effectively? Were they learning effectively? And by comparing how well each student did from the first day to the last day, I get what is known as a difference score. So for a paired samples t-test, as we get into it more, you're going to hear me talking about the importance of understanding difference scores, because you're comparing, it's not just one group versus another, it's more of a competition with yourself. Each subject, each participant, we want to see, do we see a change from time 1 to time 2, from pre-test to post-test? That's sort of the idea that we're setting up. Another type of use or application for this paired samples t-test is our second example, where we may have a comparison of two different methods of measurement applied to the same subject. What do I mean by that? Well, we're in the field of crime and law enforcement. So one of the things that we may think about is, let's imagine if law enforcement officers are doing a roadside stop and they suspect somebody of being under the influence of alcohol. Well, there's various ways that we can test your level of inebriation, or how much, to the extent that you're under the influence of something. We can do a blood test, we can do a breathalyzer, we can do a urine test, we can do a field sobriety test. So sometimes we may want to say, well, do we see a significant difference in the outcomes we get from one type of testing to another? So let's say we wanted to compare your blood alcohol level versus the reading that we get from a breathalyzer test. We could also do that with a paired samples t-test. Each person would submit both a blood test as well as a breathalyzer test, and then we would compare the outcomes for both of those to see whether or not there's a significant difference in the level of alcohol measured within their system. So the key thing with this paired samples t-test is the idea of, especially for this class, is going to be using the same group of individuals and they're exposed to two different testing situations, whether it's in the sense of a pre-test, post-test, or whether it's comparing two different methods of measurement to see which one is more effective or if we have significant differences in the outcomes. All right, so I'm going to wrap up with that for now. The key takeaways for this is understanding what the t-distribution is about, understanding the idea of the two general types of t-tests we're going to cover, both the independent samples t-test as well as the paired samples t-test. Note in both of them, the similarity is that for a t-test, it's 2. T for 2. You're comparing one group versus another. When it's an independent t-test, we're comparing one group that has performed some sort of outcome versus an independent, completely distinct second group, and then comparing the means of the two groups to see whether or not there's a significant difference. A paired t-test, the focus is much more on the differences between each individual, and usually each individual has both a measurement 1 and a measurement 2, and then we look for significant differences between them. And we're going to, after the midterm, we're going to go into much more detail about independent t-tests as well as paired t-tests. For right now, I just want to introduce you to the basic concepts of them. So that's it for today. Take care.